Welcome to Sheridan College's Introduction to Instrumentation. This lesson is a part of Module 3, Temperature Instrumentation, and will focus on thermocouples. So, what happens when the ice melts? Or the hermetic seal gets broken? You mean somebody is going to be constantly checking the water temperature and checking the seal? Really? Isn't that kind of like against the whole thing? Like we could have just looked at the thermometer. Well, somebody is. Introducing the PTC of necessity, the resistor with the persistence, the sensor of the temperature, the RTD that likes to freeze, the hero of the zero, and the one, the only, Mr. Thermistor. Yes, a thermistor. We know that they can act as a thermal switch, but we can also monitor its change in resistance and use that to calculate the temperature of the J2 and J3 junctions. We simply put the thermistor in the isothermic block, and it will measure the temperature. Hooray! For Mr. Thermistor!
This method of using thermal resistor or thermistors is called cold junction compensation. All modern temperature transmitters have this feature. So if the reference junction is measured at, say, 14 degrees, then the transmitter compensates for the shift and accurately calculates the measuring junction's voltage and hence its temperature.
The voltages produced by a thermocouple are very small. In almost all instances, they'll have to be amplified to an industry standard signal. Thermocouples can be connected to digital or analog indicators, transmitters, or controllers. Most of these devices have a cold junction compensation, so an ice bath is not necessary. This is an example of a temperature controller. There are two different wiring diagrams for two different models available. Both of them will monitor and control the process variable. Okay, in 10 seconds, identify each one. Go. Okay, time's up. If you guess that the one on the left is for an RTD, you're correct. The one on the left is for a thermocouple. This is clearly seen by the one on the left having 3, 4, and 5 connected to a device, whereas the one on the right, 4 and 5 are connected to positive and negative. Okay, here's another quick question. What is the process variable? If you said 200 degrees C, you were right. What is the set point? It's the same at 200, so right now the unit is satisfied. Here's a great example of some sophisticated technology in a little package. It's probably in your kitchen. This is an electric thermometer. Inside that little box you get a voltage to temperature conversion, in other words a transducer, a cold junction compensation, and a digital readout, all for the ridiculously low price of, well, whatever they cost. Okay, we've covered a lot of ground, so let's take a moment and do some review. First of all, the hot junction. It's not necessarily hot. It's also known as the measuring junction, which is probably a better name for it. The cold junction is not necessarily cold. It's also known as the reference junction, which is a better name for it. The Seebeck effect only generates voltage when? Well, when there's a difference in temperature between two junctions and you're using dissimilar metals to create the effect. If the measuring junction is warmer than the reference, then the voltage is positive. So by extension, what does that mean if it's negative? Well, then that means that the reference junction is warmer than the measuring junction. Okay, now we're going to spend a bit of time practicing some of the stuff we've learned.
Remember that the voltage read at the extension junction is the sum of the two other junctions, and you cannot directly measure the voltage of the measured junction at the reference junction because you are creating another thermocouple circuit.
Okay, here's our first example. A thermocoupler's measuring junction is placed in the process stream. The extension wires are extended to the voltmeter leads. This generates a measured voltage of 7.78 millivolts. Using the charts, what is the temperature? Well, before we go there, we have to ask ourselves a couple questions. First of all, what is a type of thermocouple? Well, since they're using iron and constantan, that would make it a J-type. Number two, is the J2 and J3 junctions at 32 degrees Fahrenheit or 0 Celsius? Well, they're in an ice bath, so yes. So now we can go to the chart. Okay, scouring the chart, we find 7.789, and if I look and find its location, is in the 6th column, and I shoot across to my left, and it's 140. So 140 plus 6 gives us a temperature of 146 degrees Celsius. Okay, here's one that's going to work the other way. We have a type J. What would the expected voltage be if it was 15 degrees Celsius? All right, so the first thing we do is we have to find 10 in the left-hand column. So we have our plus 10, and then we shoot across until we find the 5 column, and where they two meet, we find it reads 0.762 millivolts.